Hi you guys, so this video should be actually a little bit shorter. We're just going to do a quick introduction into a couple of the things we're going to be working on over the next several days. Alright, so when we collect data, we can make a scatter plot out of that data, and you guys have seen scatter plots before. Alright, so on the left here we have an example of a scatter plot, and the best fit line has been drawn on the scatter plot. Okay, so you can tell that the line doesn't fit perfectly. It's pretty easy to sort of see that. But one of the ways that we're going to work on to actually really give a little bit more of an explanation of why the line doesn't fit very well is called a residual plot, right? And the residual plot is this graph on the right, right? So a couple things I want to point out. All right, notice the x-axis is the same number, so 0, 10, 20, 30, 40, 0, 10, 20, 30, 40, okay? So this might be time or number of days or price of a ice cream, whatever. This is your independent variable, and then the dependent variable is on the y-axis, okay? The y-axis is different in both of these plots, so that's what we want to talk about now. Okay, so I want to point out in particular these 3 points. Okay, those 3 points there correspond with these 3 points on the residual plot. The residual plot is just a plot that shows how far each data point is from the best fit line. Okay, so I'm going to erase those circles right now and instead draw a little line. If I were going to measure how far each of those points was from the line, I would go like that, that, and that. Okay, well, those 3 distances are the same as that, that, and that. Now, obviously, the scale is a little bit different, but that's what we're measuring. Basically, we've taken this best fit line and we've moved it and kind of rotated it to be this horizontal line, and now the y-axis represents how far away from the line each of those points is. So that works as a measurement of how well the best fit line fits the data. Okay, and you can see in red here it says the curvature is more obvious in the residual plot. Okay, so when we get a residual plot that has this curved shape, okay, see how it kind of makes almost a U shape there? What that means is the data doesn't fit very well. Right. So one other thing on this slide that I want to talk about, when we say best fit line, we're actually going to learn a fancier word, right? And we call it the least squares regression line. Okay, this process of taking the data and calculating it to decide what the best fit line is called regression. So we call this a least squares regression line. Sometimes you'll see LSRL. Right? That's what we're talking about. It's just a fancy way of saying the best fit line. Okay. This next piece here is on page 143 of your binder. So if you need to pause and get that page out, you can. Okay, so let's zoom in here a little bit. So the linear regression is just the process of finding the best fit line. The process of finding the best fit line. And the least squares regression line is just the fancy word for the best fit line. Okay, now the correlation coefficient R is a measurement of how well the line, and I'll say this, the LSRL, the best fit line, fits the data. So the residual plot before was one measurement of how well the data fits the line. R, what we call the correlation coefficient, is another measurement. Okay, so R, this little table here represents R. Okay, so R can go from -1 to +1, right? -1 and +1 are both perfect correlations, okay? And 0 is no correlation. So we say off to the right, these are stronger, and these are stronger off to the left, stronger. All right, so when we use a best fit line, we can make predictions. There's two keywords here, interpolation and extrapolation. Interpolation means we're inputting an x value that falls within our data, our known values of our data. So if I measured time from 0 to 1 month, right, I could predict within 1 month, and that would be interpolation. Extrapolation means predicting outside the known values of your data. Okay, so if I measured from 0 to 1 month and then tried to make a prediction for 8 months, that would be extrapolation. Okay. Now, we're almost done here, but on the other page we saw that the residual, we saw those residual graphs, okay, or residual plot. Residuals are calculated, and this is a formula you want to remember, is observed y value minus predicted y value. And really, if you can just remember observed minus predicted, that's going to be helpful, okay? So there's a couple things we're looking for in the residual plot, right? If it shows a random pattern, like this first example here, that's a good thing. That means the data is spread out equally above and below the line, right? But when it's curved, so we get a U shape or an upside down shape, U shape, right? That means the data does not fit the best fit line very well, okay? And finally, we have this idea of correlation versus causation, okay? Correlation means there's a relationship, right? But it's not necessarily something that's causal, meaning the first thing doesn't actually cause the second thing, but they are related. So an example would be as temperature increases, so do ice cream sales. It's not that there's an actual like direct link between higher temperatures forces people to go to the ice cream store and buy ice cream. But in general, as the temperature increases, there seems to be a rise in the sales of ice cream. Okay, so that they're correlated, but it's not necessarily something that's caused by one another. Okay, this is a lot to start with. We're going to do a lot of practice with this in class and kind of give you a little more context for it. So this is meant to just be an introduction. Thanks for watching.